4.6 billion years ago, the patch of space we now call home was entirely quiet. It was just a massive, freezing cloud of gas and dust hanging motionless in the dark. By the laws of physics, a cloud like this is stable. The gravity pulling the dust particles inward is perfectly balanced by the internal pressure pushing them outward. Left to its own devices, that gas cloud would have stayed frozen forever. Something massive had to give it a push to force it to collapse. In 1969, a massive fireball streaked across the sky over Mexico, scattering debris across hundreds of square miles. This is the Allende meteorite. It's essentially a piece of physical evidence from the exact moment our solar system formed. Locked deep inside the porous surface of this rock are microscopic crystals. They are smaller than a single bacterial cell, and they are actually older than the sun itself. They are the only surviving witnesses to whatever triggered that initial collapse. When cosmochemists examined these ancient crystals, they found the stable chemical leftovers of two specific radioactive isotopes, aluminum-26 and iron-60. This graph plots the lifespan of those specific isotopes. Radioactive elements act like a ticking cosmic stopwatch. Because they are highly unstable, they break down rapidly over time into lighter, stable elements. Because aluminum-26 and iron-60 have incredibly short half-lives, they disappear quickly. They couldn't have just drifted through space for millions of years before eventually ending up in our solar system. They had to be injected into the dust cloud at the exact moment it began to collapse into our sun. That ticking clock gives us a direct physical link between the birth of our solar system and a massive cosmic engine right next door. To figure out what that engine was, we need to look at how the universe manufactures these specific heavy elements. Heavy elements are forged inside the cores of massive stars. Through a process called nuclear fusion, these stars crush light elements, like hydrogen and helium, together to build denser, heavier atoms. This requires a tremendous amount of heat and pressure. Fusing atoms into carbon, for instance, requires high-speed particle collisions at temperatures exceeding 1 billion degrees. A star will spend millions of years building up an onion-like structure of progressively heavier elements until it forms a core of solid iron. Iron is extremely stable, which means fusing it takes more energy than it produces. The star's internal furnace suddenly shuts off. Without that outward pressure to hold the star up, gravity takes over, and the entire massive structure collapses inward in a matter of seconds. That sudden, violent collapse of the core sets the stage for the most extreme explosions in the universe, and it produces the exact mechanisms that could have pushed our solar system into existence. One way this plays out is through the collapsar model. When that iron core collapses, it instantly forms a black hole. As matter swirls into this newly formed gravity well, it generates immense high-speed energy jets. These jets are so powerful that they drill their way outward, punching straight through the dense, dying layers of the massive star's outer envelope. This diagram illustrates what happens during breakout. The moment those jets breach the star's surface and hit the vacuum of space, they stop spreading out. Instead, they become highly collimated, meaning the energy is focused into an incredibly tight, narrow beam. This tightly focused acceleration acts like a cosmic particle cannon. It takes the newly forged heavy elements from the star's core, like iron-60 and aluminum-26, and blasts them deep into interstellar space at close to the speed of light. For decades, astronomers pointed to a very specific event as the trigger for our solar system, a classic core collapse supernova. The massive physical shockwave from an exploding star tearing through the interstellar medium could have easily compressed our dormant dust cloud, violently injecting it with iron-60 at the exact same time. But when researchers looked closer at the meteorites, they found a discrepancy. The actual amount of iron-60 preserved in those ancient crystals appears to be too low to match the massive output of a direct supernova hit. This led to an alternative suspect, a Wolf-Rayet star. These are gargantuan, highly luminous stars that burn through their fuel very quickly and violently shed their outer envelopes. Instead of a single sudden explosion, a Wolf-Rayet star blasts out steady, intense radiation winds. These sustained winds could have carried aluminum-26 into our neighborhood and provided the exact amount of pressure needed to nudge our dust cloud into collapsing. This is where the scientific debate stands today. Cosmochemists are still trying to determine whether our cosmic origin story was triggered by a sudden, violent shockwave or a steady, intense stellar wind, an explosive shockwave or a steady radiation wind. Both of these stellar mechanisms possess the sheer physical power required to force a dormant molecular cloud to collapse in on itself and ignite a new star. While researchers continue to analyze ancient meteorites to figure out exactly which event pushed our solar system into existence, the core reality of our origin is already clear. The heavy elements that make up the Earth's crust, the calcium in our bones, and the iron pumping through your blood right now could only have been forged inside the multi-million-degree furnaces of massive, dying stars. Every atom in our solar system is the literal radioactive fallout of a cosmic catastrophe.